Nuclear fusion is the process that powers the sun and stars, and it's often referred to as the holy grail of energy production. But what exactly is fusion? In simple terms, fusion occurs when two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. This is the same reaction happening at the core of stars, where hydrogen atoms fuse to create helium, unleashing vast amounts of heat and light. Fusion is often compared to nuclear fission, which is used in today's nuclear power plants. While fission splits heavy atoms like uranium into smaller ones, fusion works in the opposite way, combining small atoms to create a bigger one. The major difference? Fusion produces far less radioactive waste, and the fuel required, like isotopes of hydrogen, is nearly limitless and found abundantly in water. The real promise of fusion lies in its ability to generate massive amounts of clean energy. If we can master it, fusion could provide a nearly infinite energy source with minimal environmental impact, all while avoiding the risks associated with traditional nuclear power. This makes it one of the most exciting areas of energy research today. Nuclear fusion is the engine that powers the sun and every star in the universe. At the core of the sun, temperatures reach over 15 million degrees Celsius, and the pressure is immense. Under these extreme conditions, hydrogen atoms are forced together, fusing into helium and releasing an enormous amount of energy. This process is what gives the sun its incredible heat and light, and it's been sustaining life on Earth for billions of years. In a star like the sun, fusion reactions are able to occur naturally because of the extreme pressure caused by its massive gravitational force. This force pushes the hydrogen atoms close enough to overcome the natural repulsion between them, allowing them to fuse. The energy released by this fusion reaction radiates outward, reaching Earth in the form of sunlight. The challenge we face on Earth is recreating these same conditions. To make fusion happen here, we need to generate temperatures even hotter than the sun's core, up to 150 million degrees Celsius, because we don't have the intense pressure that exists naturally in stars. This is one of the key hurdles in fusion energy research, creating and maintaining the extreme conditions needed for fusion to occur, all while containing that energy safely. Fusion powers the stars, and if we can harness it, we could be looking at a future of limitless energy, just like the stars themselves. To harness the power of nuclear fusion on Earth, scientists have developed cutting-edge devices known as fusion reactors. Two of the most promising reactor designs are the Tokamak and the Stellarator, both of which are built to create and maintain the extreme conditions needed for fusion to occur. The Tokamak is the most widely researched fusion reactor design. It uses powerful magnetic fields to contain and control a superheated state of matter called plasma, which is essential for fusion reactions. Plasma, composed of charged particles, needs to reach temperatures of over 150 million degrees Celsius, far hotter than the core of the sun. In a tokamak, the plasma is confined in a donut-shaped chamber where the magnetic fields keep it from touching the walls, preventing the extreme heat from escaping. Stellarators, on the other hand, offer an alternative design to tokamaks. While they also use magnetic fields to contain plasma, they are more complex in shape, twisting the magnetic field lines in a way that can potentially offer more stability. The idea behind stellarators is to solve some of the issues tokamaks face, like maintaining plasma for longer periods, without requiring massive electrical currents. Both designs show immense promise, but they also have their challenges. Tokamaks, such as the one being developed in the ITER project, the world's largest fusion experiment, have made significant strides, yet sustaining the reaction long enough to generate more energy than is consumed remains a key hurdle. Stellarators are more complex to build, but their potential for greater stability keeps researchers optimistic. These reactors represent our best hope for unlocking the power of fusion energy. As research continues, both tokamaks and stellarators may pave the way to achieving the goal of limitless, clean energy. While nuclear fusion promises nearly limitless, clean energy, the road to achieving practical fusion power is filled with significant challenges. One of the biggest hurdles is the energy balance. We need to generate more energy from the fusion reaction than we put in to start it. Right now, fusion reactors require an immense amount of energy to heat the plasma to temperatures exceeding 150 million degrees Celsius, far beyond the heat at the core of the sun. Another major challenge is plasma containment. Fusion reactions take place in a state of matter called plasma, where atomic nuclei are moving at incredibly high speeds. This plasma must be confined long enough for fusion to occur, but because it's so hot and unstable, controlling it with magnetic fields and devices like Tokamaks and Stellarators is extremely difficult. Even slight instabilities can cause the plasma to escape, and maintaining the right conditions for an extended period has proven elusive. Additionally, the materials used to build fusion reactors must withstand extreme conditions. These materials are constantly bombarded by high-energy neutrons produced by fusion reactions, which can degrade the reactor's components over time. Finding materials that are both durable and heat-resistant is a critical area of research. There's also the challenge of scaling up fusion technology. While scientists have made remarkable progress in experimental reactors, we're still a long way from creating commercially viable fusion power plants that can provide electricity to the grid. The transition from successful experiments to large-scale energy production will require breakthroughs in reactor design, materials science, and cost efficiency. Despite these challenges, fusion energy holds enormous potential. Every year, we get closer to overcoming these obstacles, and with ongoing research and investment, the dream of limitless clean energy may become a reality. Despite the challenges, there have been exciting breakthroughs in the field of nuclear fusion that bring us closer to achieving this game-changing energy source. One of the most significant efforts is the ITER project in France, which is set to become the largest fusion experiment in the world. ITER's goal is to prove that we can achieve net positive energy, meaning more energy is generated by the fusion reaction than is needed to sustain it. If successful, ITER would be the first fusion reactor to demonstrate this on a large scale, setting the stage for future power plants. Another promising development is in the realm of private sector innovation. Companies like Commonwealth Fusion Systems and Helion Energy are pushing the boundaries with new technologies that aim to make fusion more cost-effective and faster to deploy. Commonwealth Fusion Systems, for example, is developing advanced magnetic systems using high-temperature superconductors, which could drastically improve the efficiency of plasma containment and reduce the size of future reactors. Additionally, there's been progress in overcoming the material challenges of fusion reactors. Researchers are exploring new materials, such as advanced alloys and ceramics, that can withstand the intense conditions inside a fusion reactor. These breakthroughs in materials science are crucial for building reactors that can operate for longer periods without frequent maintenance or degradation. One of the most exciting areas of fusion research is the development of smaller, more compact fusion reactors. Known as mini-fusion reactors, these designs aim to reduce the complexity and cost of fusion power, bringing us closer to commercial viability. These smaller reactors could potentially be used for localized power generation, providing clean energy to specific regions or industries. With advancements happening on multiple fronts, from large international collaborations like ITER to smaller innovative startups, the momentum behind fusion energy has never been stronger. While we're not there yet, these breakthroughs show that fusion is no longer a far-off dream, but a rapidly approaching reality. As we look to the future, the question on everyone's mind is, can we really achieve nuclear fusion as a viable, unlimited source of clean energy? The answer lies in the progress being made right now. While fusion is still in the experimental phase, with projects like ITER and private sector innovations gaining momentum, we are closer than ever to making it a reality. One of the key factors that will determine fusion's future is energy efficiency. Achieving net energy gain, where more energy is produced than consumed, is the ultimate goal. If this can be demonstrated on a large scale, the possibilities for fusion power plants could revolutionize global energy infrastructure. Once we solve the technical challenges and improve reactor designs, fusion could become the backbone of a sustainable energy future, providing electricity for homes, industries, and even entire cities without harmful emissions. Another consideration is commercial viability. For fusion to make a real impact, it needs to be scalable and cost-effective. This will require significant investments in both research and infrastructure, as well as partnerships between governments, private companies, and scientific institutions. But once the technology matures, fusion power could lead to a new energy economy, one that's not dependent on fossil fuels or subject to the volatility of energy markets. Looking ahead, fusion could also play a crucial role in addressing climate change. With zero carbon emissions and the potential to provide almost limitless power, fusion could drastically reduce our reliance on coal, oil, and gas, helping to meet global climate goals. Imagine a world where energy is abundant, clean, and available to everyone, without the environmental costs that traditional energy sources impose. Although the path to fusion energy is still unfolding, the progress being made is undeniable. We're not just talking about theoretical possibilities anymore. We're witnessing the steps toward an energy revolution. If we continue on this path, fusion could be the solution that powers the future and helps create a cleaner, more sustainable world. In conclusion, nuclear fusion represents one of the most exciting frontiers in science and technology today. It's the same process that powers the sun, and if we can harness it here on Earth, it could transform the way we produce and consume energy. Fusion offers a nearly limitless, clean, and sustainable source of power, without the harmful waste or emissions of current energy technologies. It's a bold vision for the future, but one that's becoming more realistic with every breakthrough. The road to achieving practical fusion energy is still long and full of challenges, but the progress we're seeing is incredibly promising. From the massive international collaboration of the ITER project to innovative private companies pushing the boundaries of reactor design, we are witnessing a fusion revolution unfold in real time. If successful, fusion could be the key to solving many of the world's biggest challenges, from providing clean energy to billions of people, to combating climate change. It's not just about creating power, it's about creating a sustainable future for generations to come. The promise of fusion is one of hope. Hope for a future where energy is abundant, affordable, and environmentally friendly. The next few decades will be crucial, and with continued research and investment, fusion could go from being an ambitious dream to a world-changing reality. Thank you for joining me on this journey into the future of fusion energy. If you're excited about the potential of fusion and want to stay updated on the latest breakthroughs in science and technology, be sure to like, subscribe, and hit the notification bell for more deep dives into the science shaping our world.